Page 44, guys. Shush. Gamble. Tom, can we close it, please? I've just told you that there's a pursuit question in the test. I would hope that you would be motivated enough to pay attention. Now, hold on. The best way to solve these pursuit questions is to sketch their position time graphs and solve for when they intercept. No. You can do it at home. Give yourself 20 minutes or 17 minutes. Chuck it there, Scotty. Now, commonly, the objective is to figure out the time where their positions are the same. That's just where their two curves intersect. Okay, there will be one time, a real time, maybe two times, but definitely one time where they are in the same spot. Okay, so that's why it's how long does it take for the one object to catch the other. Okay, so then if you find the time, then you can also figure out how far away the event occurred. All right, so as I said, sketching will occur easier. Now, this question is actually a little bit tricky. I started with a tricky one, but let's go. A race car 1 crosses the finishing line with a constant speed of 95. Directly ahead is another car. All right, so let's just sketch the constant speed. This is going to be S of car 1 equals V1t equals 95t. Okay? I should also probably label my axes. Okay? We're going to get to that, Hugo? Yes. Directly ahead, 150 metres, is another car travelling slower. So, boys, mathematically, we've said that further up the y-axis, we have another function with a shallower gradient. Okay? Like so. So this one now, we have to include a s-intercept, x-intercept. 85t plus 150. Okay? Now I chose this as this is now from reference of car 1 because I said that at t0 he's at 0 and the other car is ahead by 150. I could have gone the other way. I could have slid my x-axis up to the red car. The only thing that would change is instead of the 150 positive being there, you'd have a negative 150 there. And when you equate them, it doesn't really matter what side the 150's on. You could throw it over and it changes from a positive to a negative. Okay? So, in this case, there is only one time where they are in the same spot at the same time. Now, I've put a whole lot of English there, and the main straight is 650 metres long. Let's figure out how far the cars travel and is it possible? Okay, so this is the whole question. We're going to equate S1 equals to S2. And we're going to go 95t equals 85t plus 150. And so again, for this equation, there's only one possible solution. Subtract 85t from both sides. And then solve for t. Well, yeah, hold on. So, if they had an infinite amount of distance if this could go on infinitely, they would intersect at 15 seconds. But the question says they've only got 650 metres before they need to brake. This black car needs to do this before 650. So, you can throw this time back into either equation. And generally, one's going to be easier than the other. One might be a quadratic. In this case, they're both pretty easy. But we need it with reference from the start-finishing line. So we're going to use the black line and go S1. And it turns out that he needs 1425 metres. Okay? So, the answer is no. He wouldn't be able to do it. Okay? He would need 1,425 metres to approach. Hugo, can you bring all of your things and sit up here on the table, please? I don't care. Move your things, please. Because I asked you to. Thank you. Now, there is another solution. You could also do a relative velocity question. This was a very similar question. Spencer Bergsma, last chance. You're next. You'll be moving. This was very similar to the Subaru overtaking the truck question. How far along did the car travel while it was overtaking the truck? Okay, so we could do a V of one car relative to the other. Oh, look what we did. V of this car relative to that car is that take that, which is 10t. So this term, when you simplify your terms, you've got that's the relative velocity of the 95 car relative to the 85 car. So that's what you did, okay? But in a completely different way. You just equate the two functions. Now, relative velocity will only work if they're constant speeds. If they're accelerating, we can't do relative velocity because relative to one, an acceleration is still an acceleration. Okay, next. Two out-of-control trains are traveling towards each other and they start 500 meters apart. So here, we're going to have S in meters, time in seconds. One's traveling north, one's traveling south. So again, it doesn't really matter which one you assign, but we might go the north is up. So let's take train 1 as 30 north. That's going to be S of train 1. Plus 0 because we're at the 0. And then now we're going to say train 2 has a steeper gradient. It's 15. Sorry, it's not steeper. It's shallower. But he's 500 meters ahead. Okay? Now the one problem here is we don't have time. In fact, I put time in seconds. We've actually got time in hours. So I've made a slight error. I should put time in hours down here. Now in this case, you could convert. Right now, you could convert your velocities. You could convert your gradients. But if we leave it, when we solve for this, just remember that when we solve for time, it's going to be in hours. The time in hours that the trains would collide. Okay?
Does that mean we have to transfer meters into kilometers?
Well, at the end, we'll have to convert hours into seconds. Okay? So, no, you're right. My bad. We'll also need to change this into hours. Sorry. I've made this a really tricky question. Kilometers.
The other one's 0.5.
Thank you. All right, so we equate. Hopefully we've got some room in the bottom here. S1 will equal S2. Okay. Rearranging. So now when we take across 45t, look again, that's the relative velocity of the black line relative to the red line. Relative to the red line, the black line is approaching it at 45. That's going to equal 0.5. Let's try again. 0.5 over 45. 0.0111 hours. Then, well, the time and the distance. So we'll go, let's times that by 60 by 60. And we get 40 seconds. I think times it by 60, we'll get to 0.6. Yeah, 40 seconds. 40 seconds before impact. So we've just figured that one. And the distance that both trains travel. So now we've got to go, well, let's find the distance that this train travels down. Oops, I've gone too far. The distance that this train travels down and the distance that this train travels up. And we know that the two should equal, the magnitudes will be equal to 500. So where could we do that? We could go, all right, let's just chuck it here. S1 equals plus 30 times 0.0111, which equals, I'm thinking probably 330 meters, 0.333 kilometers. What just happened there? And then this one, I'm running out of room. Negative 15 by 0.111 plus 0.5. And I'm hoping that that would be negative 1666. 0.1666. Okay, so we just figured out the red displacement and the black displacement. Okay, does that make sense? That the faster travelling train would cover more distance. So if there's two trains travelling towards each other, all things being equal, they would meet in the middle. But if the one train's travelling faster, it's going to travel a greater distance relative to the other, and they're going to crash closer to the slower car. So that kind of makes sense. Okay? Oh no! A jogger. Don't ever trust joggers. They're always the ones that find the bodies. Okay. This is now a constant velocity with an acceleration. So, now we can go with s in meters, time in seconds. We have a early morning jogger with a constant velocity of 4 times time. The stationary dog, that's handy. That makes our quadratic equation or Subat equation a lot easier. Decides to chase as soon as the jogger passes. So they're in the same spot at the same time. We're going to draw a quadratic like that. Okay? Now, you'll notice there are 2 times when they're in the same spot. And if we solve for this, we might get a quadratic that gives 2 solutions for t. T equals 0. And then the final time when the dog catches back up to the jogger. Okay? So our S2 is going to be ut plus a half at squared. Well, u is 0, so we'll go a half of 1.5 t squared. Okay? And we're going to get going. S1 equals S2. 4t equals 0.75 t squared.
So what's that half?
Well, because we had to use s equals ut
Okay.
plus a half at squared, and the dog was stationary, so we set it to 0. Okay? Now, straight away, we could just cancel both sides and get the time. 5.33?
Yeah.
And that is the answer. But in that method, we didn't really get... We could factorise out a t here. What we could do is go, let's put it in quadratic form. 0.75 t squared, take 4t equals 0 plus 0. There's your quadratic. Okay, and we could do the whole negative b. So that's negative b plus or minus the square root of b squared minus 4ac. Oh, look at that. That just goes to 0. Divided by 2a, which is 2 lots, but that's 1.5. So what do we get? Plus 4, plus or minus 4 over 1.5. Oh, look at that. That's 0 or 8 on 1.5, which is 5.33. Why did I write this? 0 seconds and 5.33. Okay? Rather than me talking at you for any longer, let's have a go here. Now, I think when I made these questions, I made the velocities really, really simple such that when you convert them, I think that 14.4 divided by 3.6 is just 6.
No, that's a 21.6.
Oh, that one there is just 6. And this one here is just 4. Okay? So how about I just help you out with the tedious busy work. Let's convert everything so that we can have s in meters and t in seconds. Okay? Runner number 1 is overtaken by runner 2. So there's my S2 equals 6t. And there's my runner 1 who decides to start running. This is actually a completely different question. This is going to be 4t plus a half at squared. Now what I've done here is I've said that he needs to catch him at 50. So I've just set 50 meters. So we need to find the time and then figure out what the acceleration must be. So here the easiest one would say, well, let's go 50 equals 6t. It's a hell of a lot easier to use that because that doesn't have an unknown variable that we don't know a. So therefore t equals 8.33 seconds. So now what you're going to do is you're going to set S2 equals to S1 and calculate A. Could you do that for me, please? It won't be too tricky. Sub all the t values in, and the u values in, and the v values in. There will be one unknown, and it's equal to A, acceleration. Okay? Or just set S1 equal to 50. Yeah. But for the sake of this pursuit question, let's equate the two displacement equations and solve for the unknown. Do you work here?
So I've got the time.
So you work with
You know that oh, sorry. No, 1 sec. So that means that S1 is
S equals ut plus 1/2 at squared.
correct. All right. That's about as much time as you'd need to solve a question like this. We know that that equals 50, and then we're going to subtract the 4 by 8.33. That equals a half a t squared. Then we might divide both sides by a half t squared. That would give a. Obviously, you could do this numerically, but a equals 0.48. And that's it. To at least draw, that's his acceleration. If we wanted him to cover that 50 meters, if he needed to cover more distance in that time, i.e. cross the finishing line, the acceleration would need to be greater than 0.48. Now, again, I tried to make this realistic. These are realistic running paces, but have a think. This guy has been accelerating. And I want to, just to make sure that this is a physically possible question, what speed do you think he'd cross the line at? Well, we could do a equals v take u over t. No, t equals v. What am I doing? V equals u plus at. Let's just check this guy. Let's just go 4 plus 0.48, 8.33. It's not too much. What do we get?
7.988.
7.8.
Exactly
7.998.
I got 8. That's not that bad.
Okay, so that's a plausible running pace. It's getting up there. Obviously, he wouldn't be able to maintain that acceleration. Yeah, he's not just going to keep going faster and faster like Forrest Gump, you know, when he catches the footy ball and he keeps running at the end of the... You've all seen Forrest Gump, haven't you? It's a classic. All right, okay. So obviously, there would have to be some limit to how fast he could accelerate. Eventually, he would top out and then probably fall back down. All right. Okay. This one is really difficult, and I'm going to leave you guys to try and solve it. Okay? But first, hang on. Do we have any spare paper anywhere? Bottom of page 46. Let's do an easy one first. Then you can do the hard one. Easy one. Okay, I've got it. Here we go. We've got an elevator. A person drops a ball down an elevator shaft. So drops, U equals 0, A equals negative 9.8. And there's an elevator travelling upwards that's, let's go 20 metres below. And it's travelling upwards with a constant speed of +1 metre per second. Okay? When do they meet and where do they meet? Okay? What? Where? Where? When and where? When and where do they meet?
Where did they meet?
All right, now sketching this, we can still keep up as positive, down as negative. Okay, that's what we've got. What? Yeah. Yeah. So, there we go. Now, we're in negative territory, but we've got two equations. One's quadratic, one's linear. You equate them, find time, and then throw the time back into one or the other. But remember, whatever equation you throw the time into, you get the position relative to that object. If you put it in the elevator, you get a positive. If you put it into the rock, you get a negative. So again, you've got to consider relative to what object is the position.
Let's make some equations.
So what do we got? Minus 4.19 squared equals 1t take 20. Ooh, I think you will get 2 times. You'll get 1 real time, but if we track this back into negative time, okay, or that. Oh my god.
Is that in the matrix?
Yes.
Oh my god.
Okay.
That's crazy.
That's the ball falling. No, wait.
Rolling back down the hillside.
Back in time.
Traveling upwards in the past, striking it on while it's on its way up, going past it, and then coming back and hitting it again. Now, I think, gents and ladies, sorry, the first option where you just cancel out one time will give you the real time. But if you use the quadratic, that's when you get the 2 times. All right. So when you set it up into a quadratic form, t squared plus t plus something, and then use the quadratic solution, then you'll get a plus and minus, 1 real with a smaller value, 1 negative with a larger value. Okay. Now, I'll change the title of this to medium. Okay.
It's bulk.
Jelly roll bells.
Okay. I don't know. Is it the speed, the relative speed of their impact? I don't. B squared minus 4ac.
If it accelerates faster than gravity. Oh god. So, with the bird one, should we do t minus 2 for the bird's displacement?
There are two calculations you must do prior to setting up your graph.
Oh.
Or in order to set up your graph, you've got to
Where the
do.
meat is? Do we figure out where the meat is?
I don't know. Yes. That
Yeah.
changes things.
So you can figure out where he's throwing the meat from. No, he's doing it wrong. Nick, it looks like this.
No, I haven't done it.
That.
No, it doesn't.
Yes, it is, because the meat is quadratic. It's under the effects of gravity.
What you get is the time of impact.
Time what?
Of impact.
Of what? Dude, it's quadratic.
I'm not-
The meat
I'm
goes
not
down
yet.
with gravity. He throws it up. It doesn't just keep on going up. It's a quadratic. It's a parabola. Oh, God.
Wait, hang on.
We cooked it right. We cooked it.
Isn't that with a VT graph though?
It's fine. Let's go around and make it do this.
That's not. What's all right? That's just displacement.
Squared. It's okay, Ronnie. We're all good. Give me 1 second.
What is the discriminant of this? Anyone? Look at them all copying me down. There's no independent thought.
So independence is for chumps.
Oh, is it T-Tech 2?
Are you going to give me the discriminant, Sisson?
Thanks for your now.
Are you at double negative, so it's going to be a bigger value? Give me the, okay, but give me that. All right, now, if we wanted the negative time, we could add 19.8. Oh, this doesn't look right. Oh, you know it does. Yeah, it does. Yeah. Okay, so let's go double negative. We want the positive time. So that's minus 20.8 over minus 9.8, which is just over 2 seconds. Sounds right. What do we get? $2.11. Oh. Sounds right. Okay. This is for the elevator. This is for the elevator. So what I did from here, I set it up. You got to set it as in your quadratic form. Yeah. What's your issue, Zach?
No, never mind.
So why do you get T minus 20 first one? Because it's UT. It's VT.
Well,
VT would be 1.
it's just 1t, but he's 20 meters below the ground.
But he's not.
So it's 18.8, not 20.
No, the lift started 20 meters below the ground.
But isn't that the... Oh, yeah.
All right.
Yeah.
So you have to. I could have either gone 1t, but then I would have to put plus 20 here. So if you could have a negative 20 at one, or you've got a plus 20 at the other, but you have to have one relative to the other has to be 20 meters apart. Okay. Hey.
Do you have to use binomial expansion for the T-Tech 2 square? Oh, God.
One take 19.8 is.
Oh, negative 18.8. Ah, boy. Thank you.
So if you get the T-Tech 2 squared, can you use binomial expansion?
Say again. For this, yes. For this one, there's okay. The question is, could you solve that? Oh, that should be a highlight. Can you solve that without the quadratic? I don't think you can. So here's the problem. Year 11s. In maths, you would be given nice values that you could factorize out t and go, oh, look, you've got a 4 and a 5, and so you can solve. T equals negative 5 or plus whatever it is. Here with gravity, it's automatically 4.9. So unless I sat down and thought for a while about maybe I could give you multiples of 4.9, you might be able to factorize it. That's unlikely, okay? It's unlikely that you'll get a nice factorized squares or whatever it's called. So you'll have to use the quadratic. Yep. So you have to get from that step, set it up as the quadratic. All right. Have a go. If you pursuit questions, there's one in the test. Have a go of this really nasty one. You have to have a think about what calculations you need before you start sketching. Okay? So give that a go. I'll stop the recording here.
Oh,
It is awful.
Hugo, it is. This is gets nasty.